In this example, we are going to introduce the idea of an arbitrary interval. So rather than having fixed beginning and end points, it has floating either endpoint or both endpoints. So for the first example that we're looking at, we have the function f of x equals 3x minus 2, and we're being asked to find the net and average rate of change of this function on the interval from 3 to 3 plus h. So notice that this interval starts at 3, but then it ends like later. It ends h units later. So it's not an interval of a fixed length, but it is an interval with a fixed starting point. Okay, so let's look at net change. So I'm going to tap into our definitions from a couple of lessons ago, and this is something we've said a few times, that the net change of the function is the difference in the value the function takes on at the end and the value the function took on at the beginning. So the value the function takes on at the end is f of 3 plus h. The value the function took on at the beginning is f of 3. So this is where I hope some of the problems from homework 5 start to really kind of come back to you, because you did examples like this in homework 5 and you had lots of questions about them, and we talked about them a great deal in that week's discussion post. So f of 3 plus h, well, what does this function do to its inputs? This function multiplies its inputs by 3 and then subtracts 2. So if the input is 3 plus h, we're going to multiply that by 3 and then subtract 2. So we have 9 plus 3h minus 2, which is 7 plus 3h. Okay? And then f of 3, well, this function multiplies its inputs by 3 and then subtracts 2. So f of 3 is 7. So if we look at f of 3 plus h minus f of 3, we have, 7 plus 3h minus 7, which is the 7's cancel, and we have 3h. So what we're noticing here is that the net change depends on the length of the interval. So I want to point that out here. The length of this interval is h. And the net change depends on h. Well, let's look at the average rate of change. So remember, the average rate of change, we're taking the net change and we're dividing it by the length of the interval. So it'll be f of 3 plus h minus f of 3 over 3 plus h minus 3. Like, that's the full setup, but as I just said, that's the net change, we found it just a moment ago, over the length of the interval, which is h. So we have 3h divided by h. Oh, well, the h's cancel, so you just end up with 3. So what's up with that? Is that weird? Well, no, but it does depend on the type of function. So I want to take you back up to the very top and look at this function. So we have f of x is equal to 3x minus 2. This is a linear function. And a linear function is special for many reasons. So first of all, its graph is a line. So if we wanted to quickly sketch it, Okay, so here's a quick coordinate system. Okay, so 3x minus 2, that's already given to us in slope-intercept form. So the y-intercept is 0, -2, and then the slope is 3. So if you remember a little bit about slope, you might remember that with a slope of 3, you're going up 3 and over 1. Or you could just plot another point. For instance, you could plug in 1 for x, and you'll get that when x is 1, y is also 1. So you end up with this line. Okay? Now, as soon as you see this, I hope it makes sense why the average rate of change does not depend on the interval. No matter what interval you pick, let's just say for the sake of argument, this is A and this is B. Well, if you look at the points, AF of A and BF of B, and you look at the line connecting those points, that line is your function's graph. So it's a line whose slope is 3. So what you'll notice is that when you have a linear function, no matter what interval you pick, the average rate of change is always going to be the slope of the line that is the graph of that function. But this is only true for linear functions. And to illustrate that, we have our second example, which is not a linear function, right? It's a quadratic function, f of x equals x squared plus 5x minus 2. And we're also going to look at the net and the average rate of change. So let's look at the net. So for the net change, we're going to look at the change in the value of f at the beginning and at the end of this interval. For this example, I wanted to show you an interval where both endpoints are fluid. So this interval starts somewhere, let's call it A, and then ends later at somewhere called A plus H. So the net change is f of A plus H minus f of A. And again, this is a situation in which your work from homework 5 on just function basics becomes handy. So f of A plus H is probably something we should work out before we dive into finding the net change. So we're going to put and do to A plus H everything this function does to x. So we're going to square it, add 5 times it, and then subtract 2. So notice that everywhere that we had an x in the original function, we replaced with A plus H, and that's how we found f of A plus H. Okay, so A plus H squared, remember that's A plus H times A plus H, so that's where you're going to distribute through and combine like terms. So you'll have A squared plus 2AH plus H squared. And then here you'll distribute the 5 and then subtract 2. No like terms here, right? All of the terms are different, so we're going to leave them be. And then f of A, well, everywhere that we have an x in our original function, we're going to replace with an A. Okay, so now let's put them together. So the only thing to really be mindful of is the fact that we're subtracting f of A. So we're going to need to be sure to subtract all of f of A, so the minus is going to distribute. Now, if you want to pause the video now and write it out the way you think it's going to be, and then start the video again and make sure that you were on the right track, that would be a great idea. Okay, so here we go. So we have A squared plus 2AH plus H squared plus 5A plus 5H minus 2. So this is f of a plus h. And then we're subtracting f of a. So again, like I said a moment ago, make sure that you're subtracting all of f of a. So the minus distributes through. So what you have here is minus f of a. So you're distributing that negative through. So you'll remember when we looked at f of a plus h, we said, oh, there are no like terms, nothing combines, nothing cancels. Well, now there are some like terms, so let's label them. So we have a squared and negative a squared. So those guys are going to reduce off. We have 5a and we have negative 5a. So those guys are going to reduce off. And last but not least, we have, let's use a different color. We have negative 2 and positive 2. So those guys are going to reduce off also. So what are we left with? What is the final fully cleaned up net change? We have 2ah plus h squared plus 5h. So that is our net change. Notice that every single piece of the net change has an h in it. This is worthwhile noticing. In fact, we can even say, I see it, and I'm going to factor that h out. So you can sort of clean up the net change as h times 2a plus h plus 5. Why did I go to that trouble, right? Remember, I often say in mathematics, if you're going to do something, you do it for a reason. It's a very kind of strategy-oriented mindset. Well, let's look at the average rate of change. So remember, the average rate of change essentially takes your net change and divides it by the length of the interval. So I'm going to actually write that. I've said it a couple of times, but let's write it. So we have the net change divided by the length of the interval. Okay, so yes, I don't want to overlook the formal definition. It's f of a plus h minus f of a over h. This is all true. And then specifically for what we found, and this is where the fact that we factored that h out becomes handy. We have an h in the numerator, and we have an h in the denominator, and they will reduce off. So the average rate of change is 2a plus h plus 5. So notice for these two examples, the first example was linear, and the average rate of change did not depend on h. That was because the graph of the function was a line, and if you're talking about the slope of the line between any 2 points on the graph, which is what the average rate of change is, it's gonna be the same every time. Whereas the second example is nonlinear, and sure enough, depending on what interval you pick, depending on where you start and how long it is, the average rate of change is going to be different. So notice that the average rate of change for a nonlinear function is dependent on both the starting point and the length of the interval. So in our next example, we will look at some more functions and answering some more questions about a particular function and its net and average rate of change. And I'll actually pull a couple problems from homework to do that. All right, see you next time. Bye.